Welcome back, Design Junkies. This episode of Mechanical Engineering Made Simple comes to you by listener request. If you didn't know, we do those. So if there's a topic you want us to break down, explain, or explore, just drop us a comment. We prioritize getting the content you want in front of you. So let's dive into today's requested topic. Theory prepares you for the test. The machine shop prepares you for the moment your calculation blows up in your face.
Yeah, it really is the ultimate reality check. I mean, we spend years in academia learning how to, balance equations and run finite element analysis. And usually we do that in a quiet, temperature-controlled office.
Right, where everything is perfectly predictable.
Exactly. The math just kind of assumes a perfect universe. It assumes the steel is this flawless, homogeneous, isotropic material. And it assumes the weld is just, well, a perfect continuation of that steel.
Which I'm guessing is not how the shop floor actually works.
Oh, not even close. The shop floor doesn't care about your perfect universe. On the floor, heavy steel plate actually springs back when you try to roll it. And the heat of an arc weld, it fundamentally destroys and alters the metallurgical grain structure of the base metal.
Plus, human beings make mistakes.
Right, yeah. We are taking the pristine world of CAD models and just crashing it headfirst into the grit, the heat, and really the terrifying realities of fabricating high-pressure containment vessels.
And the forces we're trying to contain here, they are really difficult to overstate. We are talking about vessels holding thousands of gallons of boiling, volatile, highly corrosive fluids, and at hundreds or even thousands of PSI.
Yeah, a failure isn't just a leak. It's a catastrophic release of stored energy. I mean, it's shrapnel. It's lethal.
So for everyone out there actually designing these things, cutting the plate or striking the arc, this deep dive is really about bridging that gap. How does the choice made in a spreadsheet actually dictate the failure mode on the factory floor?
And that journey, well, it begins long before anyone picks up a welding torch. It starts right at the foundry with the chemical makeup of the metal itself.
Right, so let's start with the raw materials. The foundation of almost every industrial pressure vessel is ferrous metal, right? Specifically carbon steel.
Yes, but the term steel is thrown around very loosely in casual conversation. In the realm of high-stress containment, it is a highly specific, rigidly controlled chemical recipe.
For an iron alloy to even be legally and structurally classified as steel, the carbon content has to live in this really narrow band, doesn't it?
It does. It must be at least 0.02% by weight, but it absolutely cannot exceed 2%.
2% just seems like such a tiny threshold. It's kind of hard to imagine that adding 3% carbon instead of 2% completely changes the fundamental nature of the metal, what is actually happening at the atomic level if we cross that line.
Well, to visualize it, you have to look at the crystalline structure of the iron. Iron atoms, they form a lattice, basically a grid, and carbon atoms are much smaller, so they fit right into the empty spaces.
The interstices, right?
Exactly, the interstices between the iron atoms. When you keep the carbon under 2%, you are adding just enough of these smaller atoms to create, basically, roadblocks in the lattice.
Okay, so the roadblocks get in the way.
Right. They make it harder for the layers of iron atoms to slide past each other. And that resistance to sliding is what we actually measure as strength or hardness.
But the layers can still slide if they're pushed hard enough, right? Which is why steel can bend instead of breaking. It retains its ductility.
Precisely the point. Ductility is the metal's ability to deform plastically under localized stress without fracturing. But if you push that carbon content above 2%, well, you saturate the grid.
So it's not just roadblocks anymore.
No, you're fundamentally altering the compound into something called cementite. The material stops being steel and it actually becomes cast iron.
Oh, wow. Cast iron, which is incredibly hard, but it's brittle, right?
Yes, very rigid. The layers of atoms can no longer slide at all. So when a localized stress hits a piece of cast iron, say a vibration or a thermal shock, it can't yield to absorb the energy. It just cracks.
It shatters like glass.
Exactly. And for a pressure vessel, where localized bending stresses are totally unavoidable around nozzles and supports, a material that can't yield is material that will inevitably explode.
Man, so we have this strict ceiling of 2% for carbon. But the sources point out that even within true carbon steels, carbon isn't the only element the designer has to aggressively manage.
Right. Carbon is the main lever for strength, but it brings impurities and side effects. For instance, manganese is added to improve the hot workability of the steel. It binds with sulfur impurities, preventing the metal from tearing while it's being rolled hot.
But there's a cap on that too, right?
Yep, you have to cap manganese at 1.65%. If you go higher, the steel becomes way too susceptible to cracking during the rapid cooling of a weld cycle.
Okay, and what about silicon? I saw that mentioned.
Silicon is used to deoxidize the steel. It literally pulls oxygen out of the molten metal so you don't end up with bubbles or porosity in your solid plate. But silicon is capped at 0.60%.
Why is that? What happens if you add too much silicon?
Too much of it destroys the surface finish and drastically reduces the metal's toughness. And then there's copper, which sometimes sneaks in from recycled scrap. That's also capped at 0.60% because it causes a phenomenon called hot shortness.
Hot shortness, what does that look like?
The metal basically just crumbles under stress at high temperatures. It's a delicate balancing act.
It really is. But it's interesting to look backward for a moment. I mean, before we had this level of metallurgical control, people used wrought iron. You see it on old Victorian bridges or antique steam engine boilers.
Yeah.
Structurally, what is the difference between this highly controlled modern carbon steel and historical wrought iron?
The defining characteristic of wrought iron isn't just its low carbon content. It's the physical inclusion of slag.
Slag. Like the waste material.
Yeah, slag is a glassy byproduct of the smelting process created when limestone reacts with the impurities in the iron ore. In modern steelmaking, we skim that slag off completely to get a pure, homogeneous liquid.
But they couldn't do that back in the day.
Right. In the 18th and 19th centuries, the process involved physically stirring or puddling the molten iron. Small stringles of this glassy slag actually got folded into the metal.
So it'd have a grain to it, almost like wood.
Exactly like wood.
Yeah.
The slag inclusions create a fibrous structure. If you try to bend wrought iron across the grain, it's fairly strong. But if you try to pull it apart parallel to the grain, it can split right down those slag lines.
Which is fine for decorative gates because it's soft and forgivable under a blacksmith's hammer.
Sure, but when you are building a modern reactor vessel that has to withstand intense multi-directional stresses, you absolutely cannot tolerate a material with a built-in directional weakness. You need a completely isotropic material, one that is equally strong in every single direction.
It's total sense.
Yeah.
Which brings us to environments where even perfectly homogeneous carbon steel just won't survive. Like when a vessel is holding highly corrosive chemicals, carbon steel will just rust away into nothing, right?
Yeah.
So we upgrade to alloys.
Yeah, austenitic stainless steels, duplex stainless steels, high nickel alloys.
But corrosion is a broad term. A designer doesn't just ask, will it rust? The sources say they are terrified of a very specific, localized phenomenon called pitting. Why does pitting keep vessel designers up at night?
Well, general surface corrosion is annoying, but it's manageable. It's predictable. If you know a mild acid will eat away 1 millimeter of carbon steel every 10 years, you just make the vessel wall an extra 3 millimeters thick to start with. It's just a math problem.
No, you just build in a buffer.
Exactly. But pitting is an ambush. Pitting doesn't attack the whole wall evenly. It is a highly localized, aggressive electrochemical drill that creates microscopic deep holes in the surface of an otherwise perfectly shiny, uncorroded piece of stainless steel.
But wait, a microscopic hole in a piece of steel that's like 2 inches thick doesn't sound like a massive breach risk. Wouldn't it take decades for a microscopic pit to drill all the way through?
The danger isn't the pit breaching the wall and causing a leak. The danger is what the shape of that pit does to the physics of the metal around it. A microscopic pit is effectively a tiny, incredibly sharp needle pointing directly into the thickness of the metal.
Oh, I see where this is going.
Yeah, in mechanical engineering, any sharp change in geometry is a stress riser. It takes the normal, safe stress flowing through that massive steel wall and concentrates it exponentially right at the microscopic tip of that pit.
So it multiplies the stress locally.
Massively. And that spike in localized stress will initiate a crack. Once the crack starts, the pressure inside the vessel rips it open instantly. The vessel fails catastrophically. It basically unzips long before the pit ever drilled all the way through.
Man, that is terrifying. So how do you know if the expensive stainless steel you just bought is going to resist this microscopic drilling? The research brings up the pitting index, or PI. It's a mathematical formula used to calculate a metal's resistance.
Right. The pitting index is critical for material selection, especially in environments containing chlorides like seawater or certain chemical catalysts. Chlorides are the ultimate enemy of stainless steel. They aggressively attack the passive oxide layer that gives stainless its rust resistance.
Let's break down how this index is calculated. The math isn't just arbitrary numbers, right? It maps directly to what the alloy elements are actually doing. The base of the formula looks at the percentage of chromium in the metal.
Yeah, chromium is your frontline defense. It is the element that reacts with oxygen to form a microscopic, invisible, self-healing shield over the steel. So the base of your pitting index score is just the pure percentage of chromium. More chromium equals a thicker, more robust shield.
But then the formula adds the percentage of molybdenum and multiplies it by a factor of 3.3. Why does molybdenum get such a massive multiplier in the fight against pitting?
Because if chromium is the shield, molybdenum is basically the emergency patch kit. When a chloride ion manages to break through the chromium shield and starts drilling a pit, the environment inside that microscopic pit becomes highly acidic very, very quickly.
And the chromium dissolves in that acid.
Exactly, the chromium dissolves. Molybdenum, however, remains stable in reducing acids. It rushes to the site of the attack and repassivates the bottom of the pit, effectively plugging the hole and stopping the drill. Because it is so highly effective at stopping an active pit, it carries a weight 3.3 times heavier than chromium in the formula.
Wow. Okay, and then there's a third component to the equation. You take the percentage of nickel in the alloy, and you multiply it by an X factor. And this X factor is a moving target depending on the exact family of stainless steel you're using.
Right. Right. Nickel doesn't directly fight the chlorides the way chromium or molybdenum do. Instead, nickel fundamentally changes the crystalline structure of the metal. It transforms the steel into an austenitic structure.
What does that mean for the metal?
It makes the metal incredibly tough, ductile, and stable at extreme temperatures. So, if you are looking at a ferritic stainless steel, which has no nickel and a different crystal structure, the X factor is 0. Nickel plays no role.
But if you look at a duplex stainless steel, which is a hybrid structure,
For duplex stainless, the X factor is 16, and for a fully austenitic stainless steel, the X factor jumps to 30. So the math formula is Pi equals the percentage of chromium plus 3.3 multiplied by the percentage of molybdenum plus an X factor multiplied by the percentage of nickel.
and that final number is your pitting index.
Correct. Engineers look at the chloride concentration and the temperature of the fluid they're trying to contain, and they consult tables that dictate the absolute minimum Pi score the metal must possess to survive that environment.
Okay, so we've fought off the chemical attack. We have a metal that won't rust and won't pit. But a pressure vessel isn't just sitting in a vacuum, you know.
Yeah.
It gets hit, it vibrates, pumps surge and cause massive dynamic pressure spikes. What are we looking for in the material data to ensure the vessel can take a physical beating?
We are looking at two highly interrelated properties: the modulus of resilience and notch toughness.
Let's start with resilience.
Resilience is the material's capacity to act like a spring. Technically, it is the amount of strain energy the metal can absorb per unit volume without yielding. If a sudden pressure surge hits the wall needs to stretch outward to absorb that energy and then seamlessly spring back to its original shape without permanently deforming.
So a high modulus of resilience means the metal has a massive capacity to swallow those dynamic impacts.
Exactly.
And what about notch toughness?
Notch toughness is the safety net for when reality sets in. In a perfect world, your vessel has perfectly smooth, polished walls. But in reality, there might be a scratch from a grinder, a tiny undercut from a weld, or a microscopic slag inclusion. That is a notch.
The built-in weak point.
Yeah. Notch toughness is the measure of how much energy the material can absorb before a crack initiates at that notch and propagates through the metal.
I want to pause here and pull these threads together, because the sources detail a scenario that I think is probably the most dangerous trap a young engineer can fall into. I call it the fracture mechanics paradox. It is the moment where trying to make a vessel better actually guarantees it will explode.
Oh, it is a lethal oversight, and it happens when designers look at numbers on a spreadsheet without really understanding the physical trade-offs in metallurgy.
Let's walk through the exact example from the research. We are tasked with designing a thin-walled cylindrical vessel. It's roughly 3/4 of a meter in diameter. It has to hold a serious internal pressure, about 34.5 megapascals, which is around 5,000 psi.
Right, that's a serious load.
So we run the standard calculations using a standard carbon steel, and the math tells us the wall needs to be, 1.26 centimeters thick, about half an inch.
Now, half-inch steel plate is heavy. It's expensive to buy, it's expensive to ship, and it takes a lot of time and filler metal to weld together. So the designer looks at that and thinks, how do I optimize this?
And the most obvious, seemingly logical answer is to use a stronger material. I mean, if we upgrade to a high-yield strength steel alloy, the metal can take more stress before it bends. And because it can take more stress, the math allows us to make the wall significantly thinner while theoretically holding the exact same 5,000 psi.
Right, we save weight, we save money, the welds are faster. It looks like a massive win across the board.
But fracture mechanics steps in and reveals the trap. The paradox is this. As you increase the yield strength of a steel alloy, you almost always decrease its fracture toughness. Right?
Yes, you're trading ductility for raw strength. The metal becomes much harder, but it also becomes stiffer and far more brittle.
It's like trading a flexible climbing rope for a solid steel cable. The cable can technically hold more static weight, but if there's a sudden jerk, the rope stretches, while the cable might just snap.
That's a great analogy. And now apply that back to our vessel. We've built it out of this super strong, high-yield steel, and the walls are now very thin. The pressure is applied. The stress in the wall is incredibly high, but technically below the yield point.
So the math says we're safe.
But remember the reality of the shop floor. There is a microscopic flaw in that thin wall, maybe a tiny crack in the heat-affected zone of the longitudinal weld.
If the wall was thick and made of the standard ductile steel, what would happen?
In the thicker, more ductile wall, the immense stress concentrating at the tip of that microscopic crack would cause the metal immediately surrounding the crack to yield. It would stretch plastically on a microscopic level.
So it absorbs the stress.
Exactly. That stretching physically blunts the tip of the crack and absorbs the energy, stopping the crack in its tracks. The vessel survives.
But with our optimized thin high-yield wall.
The high-yield steel doesn't want to stretch. It's too stiff. It lacks the fracture toughness. So when that same stress concentrates at the crack tip, the metal can't yield to absorb it. Instead, the crack propagates.
And because the wall is thin.
Because the wall is so thin, there isn't enough material volume to arrest the running crack. The crack shoots across the entire length of the vessel at the speed of sound, and the vessel detonates. The designer, by choosing a stronger material to save weight, actually engineered a bomb because they ignored the relationship between yield strength and fracture toughness.
Man, that is deeply unsettling. I mean, if I am the welder on the floor, I am just following the procedure. I look at the blueprint, I see the thin plate, I grab the specified filler metal, and I lay down what looks like a visually flawless weld. But you were saying that even with a perfect weld, the vessel is fundamentally unsafe before I even strike an arc, purely because of a blind spot in the design office.
Yes, unfortunately. The welder can do everything right, but if the material architecture lacks the inherent toughness to tolerate the microscopic imperfections that exist in all fabricated structures, the system is doomed. You cannot evaluate a material based solely on its ability to resist yielding. You have to evaluate how it behaves when it inevitably fails locally. Does it yield and forgive, or does it snap and destroy?
Right, and that transition from the microscopic crystal structure of the metal to the macro-level physics of the vessel brings us to the next massive hurdle. We know what metal we are using. Now we have to figure out how to shape it to survive.
The architecture of containment. And the very first dividing line in pressure vessel design philosophy is establishing the mathematical boundary between a thin-walled vessel and a thick-walled vessel.
And this isn't just a visual distinction, like looking at a soda can versus a scuba tank, right? There is a rigid mathematical ratio that changes the entire physics of the analysis.
It is the radius to thickness ratio. You take the internal radius of the cylinder and divide it by the thickness of the wall. If that ratio is greater than 10, you are operating in the thin-walled universe. This is where the vast majority of industrial storage tanks, distillation columns, and standard pressure vessels live.
Why is the number 10 the magic threshold? What changes mechanically at that point?
It's about how the stress distributes through the metal. In a thin-walled vessel, we assume that the membrane stresses, which are the forces acting tangentially to the surface, basically pulling the metal apart like a stretch balloon, we assume those are completely uniform across the entire thickness of the wall.
So the inside skin of the steel and the outside skin of the steel are experiencing the exact same amount of tension.
Exactly. Because the wall is relatively thin, we can also mathematically ignore the radial stress.
Radial stress being the direct outward push of the fluid against the inside face of the steel, right?
Correct. It's compressing the wall outward. In a thin-walled vessel, the membrane tension tearing the wall apart is so massively dominant that the radial compression is basically negligible. But if your radius to thickness ratio drops below 10, say you have a high-pressure reactor with incredibly thick walls, everything changes. You are now in thick-walled territory.
And the uniform stress assumption just goes out the window.
Completely. In a thick-walled vessel, the radial stress becomes a massive factor. And more importantly, the membrane stress is no longer uniform. The tension on the inside skin of the vessel is significantly higher than the tension on the outside skin.
Oh, so it's uneven.
Very uneven. The stress creates a steep gradient through the thickness of the steel. The math required to ensure the inner layers don't tear while the outer layers are barely doing any work is vastly more complex.
But for the sake of our primary focus today, we are staying in the thin-walled uniform stress universe. We have our calculated stress. The next step is to compare that stress against the material's limits to see if the vessel will survive. And the sources present two competing schools of thought on how to predict failure: the maximum stress theory and the maximum shear stress theory.
Right, these theories are attempts to mathematically model exactly how a piece of metal gives up. The maximum stress theory is the oldest, simplest, and most historically widespread. It is actually the foundational theory behind the incredibly ubiquitous ASME Boiler and Pressure Vessel Code, Section VIII, Division 1.
Okay, so how does the maximum stress theory view failure?
It looks at the world in one dimension at a time. It states that failure occurs the moment the maximum principal stress in any single direction exceeds the simple tensile yield strength of the material. Imagine pulling a steel bar straight apart. The theory says, I only care about the force pulling the bar. If that force exceeds the limit, it breaks. I don't care what is happening in the other directions.
Which sounds incredibly logical, honestly. If you pull it too hard, it breaks. Why would you need another theory?
Because that logic only holds true for brittle materials like cast iron or glass, which actually do fail by pulling straight apart. But remember our entire discussion about carbon steel and ductility?
Right, the layers sliding?
Exactly. Ductile metals rarely fail by just snapping in pure tension. They fail by slipping, they deform plastically, and that plastic deformation is driven by shear forces, not pure tensile forces.
I want to make sure this is crystal clear for everyone. If I am pulling a piece of ductile steel straight apart, end to end, the tension is horizontal. But you are saying the metal isn't actually failing horizontally.
That's right. It's failing diagonally.
Yeah.
When you pull that bar, the crystalline lattice we talked about earlier starts to slide. And the mathematical maximum shear stress, the force trying to slide the atomic layers past one another, always occurs on a plane that is exactly 45 degrees angled away from the direction you are pulling. Think of a deck of cards. If you push the top of the deck sideways, the cards slide over each other. That is shear. Ductile metals fail by shearing along those 45-degree slip planes long before the pure tensile stress reaches its absolute maximum limit.
So the maximum shear stress theory accounts for this. It looks at the interaction of stresses in multiple directions to predict when that diagonal slip will actually occur.
Yes. The maximum shear stress theory states that yielding begins when the maximum shear stress at a given point reaches 1/2 of the uniaxial yield strength. It is a much more accurate representation of reality for the ductile alloys we use in pressure vessels.
To put this in everyday terms, it's like evaluating a rope bridge. The maximum stress theory just looks at the total weight on the bridge. But the maximum shear stress theory looks at the weight, and it also considers the wind blowing the bridge sideways and the friction of the ropes grinding against each other. It realizes that the combination of forces is what actually frays the rope.
That is an excellent way to conceptualize it, yeah. The interaction of forces is the real killer.
But if the shear stress theory is more accurate for the metals we actually use, why does the most famous engineering code in the world, ASME Section VIII, Division 1, still use the older, less accurate maximum stress theory?
It comes down to the philosophy of design by rules versus design by analysis. Doing a full multidirectional shear stress analysis on every single square inch of a complex vessel, around every nozzle, every support bracket, every change in thickness, requires immense computational power and highly advanced finite element analysis. Decades ago, that just wasn't possible. So the ASME code adopted a pragmatic approach.
The design by rules approach.
Right. The code basically says, we know the maximum stress theory is a simpler, slightly less accurate model. We know there are localized secondary bending stresses around the nozzles that we aren't explicitly calculating. To compensate for this mathematical ignorance, we're going to impose a massive global safety factor. You use the simpler formulas, but the code artificially drastically lowers the allowable stress you were permitted to use.
So the penalty for easier math is buying way more steel.
Exactly. The vessel ends up significantly thicker, heavier, and more expensive than it theoretically needs to be. But that massive thickness acts as a brute force blanket, absorbing all those complex shear and bending stresses that the simpler math ignored. It's an incredibly safe, conservative way to build, but it is definitely not optimized.
Okay, so the walls are thick, but what about the overall physical shape? If a facility says they need a vessel to hold 10,000 gallons of pressurized gas, does the designer just arbitrarily pick a length and a width?
Not at all. Geometry dictates material efficiency. You're always trying to maximize the internal volume while minimizing the surface area, because surface area equals tons of expensive steel. If you are building an atmospheric storage tank, say a massive diesel tank with zero internal pressure, the optimum length to diameter ratio, or L over D, is 1.
Wait, an L over D of 1 is essentially a cylinder that is exactly as wide as it is tall, like a giant soup can.
Exactly. A perfectly spherical shape would be the absolute maximum efficiency, but building a giant sphere out of flat plate is a nightmare of welding and fabrication. A cylinder with an L over D of 1 is the most cost-effective compromise for atmospheric storage.
But the moment you introduce pressure, the shape has to stretch out, right?
Yes. For pressurized vessels, the flat ends, the heads, become incredibly thick and expensive to handle the outward thrust of the pressure. To minimize the cost of those massive heads, you make the diameter smaller and stretch the length of the cylinder out.
So it becomes more tube-like.
Yeah. For standard pressurized vessels with a wall thickness under 2 inches, the optimum L over D ratio is generally 6. If the pressure is so extreme that the walls are over 2 inches thick, the optimum ratio stretches all the way out to 8. You get these long, slender, bullet-shaped tanks.
But we've only been talking about internal pressure trying to blow the tank apart. The research dives deeply into the inverse problem, which honestly sounds far more terrifying mechanically.
External pressure. External pressure is a completely different physical regime. Internal pressure places the steel in tension. Steel loves tension. It naturally wants to pull taut and stable. External pressure places the steel in compression. The atmosphere is literally trying to crush the vessel inward.
When would a heavy industrial vessel ever experience external crushing pressure? Are we talking about submarines?
Submarines are the classic example, sure, but in a chemical plant, it happens constantly. A vessel might be operating under a design vacuum to lower the boiling point of a chemical, but the most dangerous scenario is accidental vacuum during routine maintenance.
How does that happen?
Well, you have a massive vessel that has just been cleaned with live superheated steam. The entire interior is full of hot steam. The maintenance crew shuts the valves and goes to lunch. As the vessel cools, the steam condenses back into a tiny puddle of liquid water.
And because the water takes up a fraction of the volume of the steam, it pulls a massive vacuum inside the sealed tank.
A near-perfect vacuum. Suddenly, you have the full weight of the Earth's atmosphere, 14.7 pounds on every single square inch of the vessel's surface pushing inward.
I understand the physics of the vacuum, but here's what I struggle with. We are talking about vessels built with half-inch or 1-inch thick, solid steel walls. How can near-atmospheric pressure crush solid steel? The stress can't possibly exceed the yield strength of the metal.
That is the terrifying beauty of external pressure. It doesn't need to exceed the yield strength of the metal. External pressure causes a failure of geometric instability, not material strength. We call it buckling.
How does buckling bypass the strength of the steel?
Think of an empty aluminum soda can. If you stand perfectly straight on top of it, the microscopically thin aluminum wall can actually support your entire body weight in pure compression. The material is strong enough. But if someone walks by and taps the side of the can with a pencil, introducing a tiny dent, a geometric imperfection, the entire cylinder instantly collapses and crushes flat.
Because the shape failed.
Exactly. The material didn't get weaker. The geometry became unstable. A massive steel vessel is exactly the same. The rolling machines on the shop floor can never create a mathematically perfect circle. There is always a slight out of roundness. When external pressure hits that slightly flattened area, the geometry becomes unstable, and the massive steel wall instantly buckles inward, folding like paper at a stress level far below what the metal could theoretically handle.
So how do you stop a 50-foot long steel cylinder from buckling under vacuum?
You have to fundamentally change its geometry. Designers use stiffening rings. These are heavy steel I-beams or thick plates welded edge-on around the outside circumference of the vessel.
What do those rings actually do?
What these rings do is effectively break one long, mathematically vulnerable cylinder into a series of very short, incredibly stiff cylinders. The short distance between the rings prevents the buckling wave from ever forming.
But there's a massive red flag on the shop floor regarding these rings, right? The placement isn't arbitrary at all.
Oh no, it is a cardinal rule of fabrication. Stiffening rings must never ever be welded directly over a circumferential weld seam joining two sections of the shell.
Because welding the ring over the shell seam means you are stacking heat-affected zones.
Exactly. You are crossing a massive circumferential weld with all its residual stresses and potential internal flaws with two more fillet welds to attach the ring. You are creating a metallurgical nightmare of overlapping brittle zones and multi-directional stress concentrations. If a crack is going to start anywhere, it will start there. The rings must always be offset from the shell seams.
Okay, so the vessel is designed. The walls are thick enough to handle the tension. The rings are spaced to prevent the buckling. Now we have to actually stand this massive structure up and support it. The sources detail several ways to do this, starting with skirts. Why are skirts the gold standard for vertical vessels?
A skirt is brilliantly simple. It is just a cylindrical continuation of the vessel's shell that extends downward and bolts to the concrete foundation. The reason it is the gold standard is load transfer. If you make the diameter of the skirt exactly match the diameter of the vessel, the massive dead weight of the vessel transfers straight down the walls directly into the foundation. There is no offset, which means there are minimal discontinuity stresses.
But wait, the vessel might be operating at 800 degrees Fahrenheit while the concrete foundation is at ambient temperature. Doesn't that extreme temperature difference travel down the steel skirt and cause problems?
Oh, it causes enormous problems. The thermal gradient creates massive bending stresses right at the weld joint where the hot vessel meets the cooler skirt. The metal is trying to expand and contract at different rates in the exact same location. To mitigate this, engineers use a hotbox design.
How does that work?
They weld the skirt on, and then they pack the top few feet of the skirt both inside the cylinder and outside with heavy insulation.
What does that insulation do?
It prevents the immediate area below the weld from cooling down too quickly. It forces the temperature drop from 800 degrees to ambient to occur gradually over the length of the skirt, rather than violently right at the weld seam. It spreads the thermal strain out over a large area, relaxing the stress.
That is a very elegant solution. What about legs? You see smaller tanks standing on 3 or 4 legs all the time.
Legs are cheap and easy, which is why you see them on smaller low-pressure tanks. But mechanically, they are a nightmare. Instead of spreading the load evenly around a continuous cylinder, like a skirt, a leg concentrates the entire weight of the vessel, the fluid, and the wind loads into 3 or 4 tiny localized patches on the thin shell wall.
They act like hole punches.
Exactly right. They punch into the shell. If the legs are longer than about 7 feet, the bending moments get so high that you have to weld cross-bracing between them to keep them from splaying out. But the real danger is dynamic loading. If a vessel is mounted on a vibrating compressor platform or has an internal agitator violently mixing fluids, you should never use legs.
Why not?
The rhythmic vibration will cause the localized stress patches where the legs meet the shell to fatigue, and the legs will literally tear a hole right out of the side of the tank.
Yikes. And for massive horizontal vessels,
Yeah.
we aren't standing them on end. They're lying flat like a submarine.
For horizontal vessels, you'd use saddles for the dead weight. But if the vessel is located in an earthquake zone or a hurricane zone, you have massive lateral shear forces trying to rip the vessel off its foundation. For that, you use ring girders.
How do those differ from saddles?
A saddle just cradles the bottom half of the tank. A ring girder is a massive, rigid steel hoop that completely encircles the vessel. The vessel sits inside the hoop, and the hoop is anchored to the steel framework of the facility. When a seismic wave hits, the violent horizontal shear force is transferred from the thin skin of the vessel into the massive rigidity of the ring girder and down into the foundation, preventing the thin shell from twisting and tearing open.
It is incredible how the entire architecture of the vessel has to fight a war on 2 fronts. The chemical and pressure war on the inside, and the gravity, wind, and thermal war on the outside. But all of this brilliant CAD architecture is completely useless if the pieces aren't put together perfectly. Which brings us to the next, arguably most critical phase. Once the geometry is finalized, it's time to cut plate and strike an arc.
The assembly phase. Yeah, this is where the mathematical theory meets the molten reality of the weld pool. And the bridge between those two worlds is a concept called joint efficiency.
Joint efficiency.
Yeah.
In the math, it is represented by the Greek letter eta. What exactly is eta measuring?
Eta is a blunt mathematical ratio. It is the strength of the welded joint divided by the original strength of the solid parent plate. It asks the basic question: how much damage did we do to the structural integrity of this steel cylinder by cutting it in half and melting it back together?
So a perfect score would be 1.0, 100% efficiency.
Yes. If you have a fully penetrated double-sided butt weld and you perform 100% volumetric radiographic testing, meaning you X-ray every single millimeter of the weld to prove there is not a single microscopic pore or slag inclusion inside it, the code grants you an eta of 1.0. The math treats the cylinder as if it were a seamless, continuous piece of steel.
But X-raying miles of weld seam on a massive vessel is incredibly expensive and time-consuming. What if the client doesn't want to pay for all that testing?
The code allows it, but it heavily penalizes the design. If you only spot check the welds, or if you use a less reliable joint design like a single-sided weld with a backing strip, the code will arbitrarily drop your joint efficiency factor. Your eta might drop to 0.85 or even 0.70. The code assumes that because you didn't prove the weld is perfect, it is inherently flawed.
And how does that penalty actually manifest in the design? Does the designer just accept that the vessel is weaker?
Oh no, the vessel still has to hold the design pressure. The penalty is financial and physical. If your weld is only considered 70% as strong as the base metal, the only way to make the weak weld strong enough to hold the pressure is to make the entire vessel thicker. You have to specify vastly heavier, thicker, more expensive steel plates for the whole project just to compensate for the theoretical weakness of the cheaper, uninspected welds.
How?
It's a direct trade-off between the cost of non-destructive testing and the cost of raw steel.
Let's look closely at those welds, because here's a concept from the sources that completely blew my mind. When you build a cylindrical vessel out of rolled steel plates, you have two types of welds. You have longitudinal welds, which run straight down the length of the cylinder from end to end, and you have circumferential welds, which wrap around the cylinder like a belt, joining the ends of the cylinders together. I always assumed all the welds were under the same pressure, but they absolutely are not.
No, they're not. The stress distribution in a pressurized cylinder is highly asymmetrical. And the math behind it is elegant, but the implications are terrifying.
Let's break down the two forces. We have longitudinal stress and we have hoop stress.
Right, longitudinal stress is the force trying to stretch the cylinder lengthwise, basically trying to blow the two end caps off. Hoop stress, also known as circumferential stress, is the force trying to expand the diameter of the cylinder. It is trying to tear the cylinder open like a bursting pipe.
And the staggering fact is that the hoop stress is exactly twice as large as the longitudinal stress. Why is that? Why is the pressure fighting so much harder to expand the diameter than it is to blow the ends off?
It comes down to the surface area the pressure is acting against compared to the amount of steel available to hold it back. Think about the longitudinal stress first. The pressure is pushing against the flat circular area of the end cap. The steel fighting that pressure is the entire circumference of the cylinder wall.
Okay, that makes sense.
Now, think about the hoop stress. Imagine slicing the cylinder in half lengthwise. The pressure is pushing against the massive rectangular projected area of the entire length of the tank, but the only steel fighting that massive outward push is the two thin cross sections of the wall you just cut. Because the projected area trying to split the tank is so much larger relative to the resisting steel, the resulting stress is exactly double.
So the hoop stress is twice as intense. Now, apply that back to the physical welds on the shop floor.
This is where it gets critical. Look at the orientation of the welds. The circumferential welt, the belt wrapping around the tank, is oriented perpendicular to the longitudinal stress. It is only fighting the force trying to blow the ends off, which is the weaker stress.
But the longitudinal weld, the straight seam running end to end, is oriented exactly perpendicular to the massive hoop stress.
Exactly. The longitudinal weld is taking the absolute worst of the beating. The force pulling across that seam is double the force pulling across the circumferential seams. The hoop stress is violently trying to rip that specific weld apart.
So that's why vessels fail the way they do.
Yeah, this is why when a cylindrical vessel fails from overpressure, it almost never pops its end caps off like a champagne cork. It splits straight down the side, down its length like a hot dog expanding on a grill. The skin of the hot dog splits lengthwise because the hoop stress exceeds the strength of the casing before the longitudinal stress can blow the ends off.
Because of this dynamic, the longitudinal welds are by far the most critical joints in the entire structure. They are the weak links holding back the most terrifying forces.
They require the highest quality filler metal, the strictest heat controls, and the most rigorous X-ray inspections. A flaw in a circumferential weld is bad, but a flaw in a longitudinal weld is catastrophic.
If the longitudinal weld is this massive vulnerability holding back double the stress, my immediate question is, why don't we just get rid of it? Why don't we just forge seamless cylinders for everything? Just cast a solid pipe and cap the ends.
It's a great question. And for extremely high-pressure, specialized applications like deep-sea submersibles or high-caliber artillery barrels, we actually do use thick-walled monoblock forgings. They take a solid, glowing ingot of steel and use a massive hydraulic press to pierce a hole straight through the center, creating a completely seamless tube.
So why not do that for everything?
Because you cannot do that for a refinery distillation column that is 20 feet in diameter and 150 feet tall. The scale is impossible, and the cost of forging something that massive would bankrupt the project. For industrial scale, you have to buy flat steel plates, roll them into arcs, and weld them together. The longitudinal seam is an unavoidable reality of scale and economics.
And we also have to deal with the unavoidable reality of time. I mean, we build this vessel, it's perfectly welded, and we put it into service. But steel rusts. How does a designer mathematically guarantee that a vessel won't burst 20 years from now when half the steel is corroded away?
They use a concept called the corrosion allowance, denoted by the letter C. The designer does all the complex math we just discussed to figure out exactly how thick the steel needs to be just to hold the pressure. Let's call that thickness T. Then they consult the chemists to determine how fast the specific fluid will eat the steel.
Oh, so they calculate a specific rate of decay.
Right. If they calculate it will lose 3 millimeters of steel over a 20-year lifespan, they add 3 millimeters of sacrificial steel to the design. The plate they buy is T plus C.
But here is the critical rule from the sources. When they are running the stress calculations, checking for buckling, calculating the joint efficiency, which number do they use?
They must, by law, use the end-of-life thickness, which is T minus C. You completely ignore the sacrificial metal in all your strength calculations. You have to mathematically prove that the vessel is structurally safe and compliant on the very last day of its intended 20-year life, when all that extra metal has rusted away into nothing.
It's literally engineering for the worst-case scenario. And speaking of worst-case scenarios, let's look at what happens when the rolled plates don't actually line up perfectly on the shop floor. I mean, the CAD model shows perfectly aligned cylinders abutting perfectly spun dished heads, but we are bending 2-inch thick steel plate.
Right, and heavy steel plate has a memory. When you run it through the massive 3-roll bending machines, you overbend it slightly because when it rolls out, it springs back. Getting a perfectly true, mathematically precise circle is virtually impossible. So when the fitters try to butt two large rolled cylinders together, the edges don't match up perfectly, one lip sits higher than the other. This is called misalignment.
Why is misalignment so dangerous? Can't the welder just lay a really thick, wide bead of filler metal over the gap to smooth it out?
You can visually smooth it out, sure, but you cannot hide the physics. When the vessel pressurizes, the enormous internal force tries to force the misaligned, slightly out of round cylinders into a perfect, true circle. This violent shift creates massive, localized bending stresses exactly at the weld joint, tearing at the root of the weld from the inside.
So it's constantly prying at the weld.
Yes. That is why the tolerances for misalignment are incredibly strict. The code might dictate that the offset cannot exceed the thickness of the plate divided by 10, up to an absolute maximum of maybe 5 millimeters.
And if the fit-up is worse than 5 millimeters?
The inspector halts the job. You have to cut the tack welds, hook the plates back up to the cranes, use massive hydraulic jacks and strong backs to physically force the steel into alignment, and try again. You cannot bridge bad geometry with weld metal.
Knowing that the longitudinal weld is holding back the massive hoop stress, and knowing that any misalignment is actively trying to pry that joint apart, the actual process of melting the steel and laying that bead of filler metal is paramount. The theory has taken us as far as it can. Now we need the sparks.
Exactly. This is the metallurgy in action. Welding is not just gluing metal together. It is a highly localized, rapidly cooling, continuous casting process. You are literally melting the base plates and adding a third molten alloy into the mix to fuse them.
The sources outline a few specific welding processes used in vessel fabrication. Let's start with the workhorse, SMAW.
ASME U stands for Shielded Metal Arc Welding, universally known on the shop floor as stick welding. It is the oldest and most versatile process. The welder holds a stinger with a consumable electrode rod. The rod is a solid metal core covered in a thick coating of chemical flux. You strike an arc, and the intense electrical heat, upwards of 10,000 degrees, melts the metal core to provide the filler into the joint.
But what is the point of the flux coating? Why not just use a bare wire?
If you melt steel in the presence of the open atmosphere, the oxygen and nitrogen in the air will instantly dissolve into the molten puddle. When the puddle freezes a second later, those gases get trapped inside the solid steel, creating thousands of tiny bubbles. This is called porosity, and it turns the weld into Swiss cheese.
So the flux stops that.
Yes, the flux coating solves this. As the heat of the arc melts the rod, it also burns the flux. This combustion evolves a cloud of shielding gas that physically pushes the atmosphere away from the liquid puddle.
Stick welding is incredibly common for field work, right? Like erecting tanks outdoors.
Yeah, because that cloud of burn flux is very robust. A slight breeze outdoors won't blow it away. The downside is that the burn flux leaves a thick, hard layer of glassy slag over the top of the finished weld bead. The welder has to manually chip and wire brush every single millimeter of that slag away before they can lay down the next pass.
And if they don't?
If they miss a spot and weld over a piece of slag, it gets permanently trapped inside the joint. That is a slag inclusion, a severe physical defect that acts as a crack initiator.
To avoid that slag, shops often use TIG welding, right?
Yeah.
Gas tungsten arc welding.
Right. TIG is the surgeon's scalpel. It is entirely different. The torch uses a non-consumable tungsten electrode. The tungsten doesn't melt. It just carries the electric arc to heat the base metal. The welder holds a separate bare filler rod in their other hand and manually dabs it into the molten puddle. There is no flux.
So how do they shield the puddle from the air?
The torch constantly blows a steady stream of pure inert gas, usually argon or helium, out of a nozzle to shield the puddle.
It requires an immense amount of manual dexterity. Both hands are doing completely different things.
It is the most difficult manual process to master, but it produces the highest quality, most precise, flawlessly clean welds. There is no slag to chip and no spatter. It is heavily used for the root pass, the very first, deepest, most critical layer of a weld joint at the bottom of a thick plate, and it is the primary process for welding exotic, highly reactive alloys like titanium or superaustenitic stainless steels, but it is very slow.
And the sources also mention an evolution of TIG called plasma welding, which honestly sounds like a sci-fi weapon.
It operates on similar principles to TIG, using a tungsten electrode, but the physics of the arc are drastically altered. In plasma welding, the arc is constricted and forced to pass through a tiny, water-cooled copper nozzle. This constriction radically increases the velocity, the density, and the temperature of the plasma arc. It creates a tightly focused, incredibly intense beam of heat.
What does that focused beam allow you to do?
It allows for something called a keyhole effect. The plasma beam is so intense it literally punches a tiny hole completely through the entire thickness of the steel plate. As the automated torch moves forward, the molten steel flows around the edges of the hole and seamlessly closes up behind it. It allows for incredibly deep, narrow penetration on thick plates in a single pass with very minimal distortion.
But regardless of whether you use stick, TIG, or plasma, the intense heat of the arc does something fundamental and permanent to the solid steel adjacent to the weld, the heat-affected zone, or HAZ.
Yeah, the HAZ is the invisible casualty of welding. It is the narrow band of base metal immediately next to the molten puddle. This metal didn't get quite hot enough to melt, but it got extremely hot, perhaps 2,000 degrees. And then it was rapidly quenched as the massive volume of surrounding cold steel sucked the heat away.
What does that rapid thermal shock do to the crystalline lattice we talked about earlier?
It traumatizes it. The rapid heating and violent cooling alters the microscopic grain structure of the steel in the HAZ. It often makes that narrow band of metal significantly harder, stiffer, and vastly more brittle than the rest of the plate. It locks massive residual tensile stresses into the metal. When a welded pressure vessel fails, the crack almost never starts in the weld metal itself. It almost always originates in the brittle, highly stressed, heat-affected zone just outside the weld.
Aside from the invisible metallurgical damage of the HAZ, we also have to worry about the physical, visible flaws caused by the welder's technique. We talked about porosity and trapped slag. The sources highlight another major defect: Undercut. Explain what undercut looks like and why it's so dangerous.
Undercut is a classic visual defect. It happens when the welder is moving too fast or using too much amperage. The intense heat melts a small trench or groove into the solid base metal right at the outer edge, the toe, of the weld bead. But the welder moves on before the molten filler metal can flow in and fill that groove back up.
Yes. So you are basically left with a permanent ditch carved into the base metal alongside the weld.
Yes, and it is incredibly dangerous for two distinct reasons. First, you have literally carved away parent metal. If the wall needed to be 1 inch thick to hold the pressure, the undercut has gouged it down to 0.9 inches at that exact spot. The wall is physically thinner.
And the second reason?
The sharp V-shaped geometry of the undercut groove acts as a severe stress riser. It concentrates the hoop stress exactly at the thinnest, most damaged point of the metal, right next to the brittle heat-affected zone. It is a perfect storm for initiating a crack.
So, given how incredibly sensitive the metallurgy is, and how easily a welder can accidentally carve a stress riser or trap slag, how does a manufacturer guarantee that the person holding the torch actually knows what they are doing? They can't just take a welder's word for it when lives are on the line.
Absolutely not. In pressure vessel fabrication, every single spark is dictated by a mountain of highly controlled legal paperwork. And that paperwork starts with the WPS, the Weld Procedure Specification.
The WPS is essentially the recipe for the weld.
It is an exhaustive recipe. A welding engineer writes the WPS, and it dictates every single variable. It specifies the exact grade of base metal, the exact AWS classification of the filler rod, the precise range of amperage and voltage allowed, the travel speed, the angle of the joint preparation, the flow rate of the shielding gas. The welder is legally bound to follow it.
But a recipe on paper doesn't prove that the resulting cake is edible. How do you prove that the engineering assumptions in the WPS actually result in a weld that can hold 5,000 psi?
You prove it with violence. You generate a PQR. A procedure qualification record. A master welder takes the newly written WPS, goes into the shop, and welds 2 pieces of heavy scrap plate together following the recipe exactly. Then that test plate is subjected to brutal destructive testing in a laboratory.
What do they do with it?
They X-ray it to check for porosity. Then they cut it into strips. They put those strips into a massive hydraulic tensile tester and literally rip the steel apart. They measure exactly how much force it took to snap it, proving it meets the minimum tensile strength. Then they take other strips and put them in a bending jig, violently folding the weld completely in half into a U shape. This proves the weld and the HAZ have the required ductility and won't crack under localized strain.
Only if the test plate survives all of that destruction does the recipe get approved.
Exactly. If the PQR passes, the WPS is legally certified. And only then can a welder take a performance test using that WPS to see if their hands are steady enough to execute it.
Welding is essentially localized, extreme metallurgy. And sometimes controlling that metallurgy means controlling the temperature of the entire vessel before and after the welding happens. Let's talk about preheating and PWHT. Why would you take a blowtorch to a piece of steel before you start welding it?
It's all about controlling the cooling rate. If you are welding a very thick 3-inch plate of carbon steel, that plate is a massive heat sink. When you strike an arc, the tiny molten puddle is surrounded by hundreds of pounds of cold steel. The moment the arc moves, the cold steel violently sucks the heat out of the puddle. That rapid quench is what creates the hard, brittle microstructures in the HAZ we talked about.
So preheating softens the blow.
Exactly. Using giant rosebud torches or electric heating pads, you heat the entire joint area up to, say, 300 or 400 degrees Fahrenheit before you strike the arc. Now, when the puddle freezes, the surrounding metal is already warm. The cooling rate is drastically slowed down. The metal cools gently, allowing a soft, ductile grain structure to form instead of a brittle one.
It's exactly like the analogy of the frozen glass. If you pour boiling water into a frozen glass, the thermal shock shatters it. If you warm the glass in the sink first, it survives.
Right. Perfect analogy.
And what about post-weld heat treatment? PWHT. The weld is done, the vessel is built. Why put it in an oven?
Because the vessel is acting like a coiled spring. Even with preheating, the localized expansion and contraction of thousands of weld passes has locked massive residual tensile stresses into the joints. The vessel is fighting itself. PWHT involves rolling the entire finished vessel into a massive gas-fired furnace. You slowly bring the entire structure up to a dull red heat, maybe 11 or 1200 degrees Fahrenheit, and you let it soak at that temperature for hours based on the thickness of the steel.
And at that temperature, the steel is soft enough to relax.
Precisely. The yield strength of the steel drops so low at that temperature that the locked-in residual stresses literally force the metal to microscopically creep and yield. The stresses relieve themselves. Then, you very slowly cool the furnace down over several days. The vessel emerges structurally relaxed, dimensionally stable, and incredibly tough.
Before we leave the shop floor, I want to touch on one specific detail from the sources regarding external attachments. The vessel is designed to hold pressure, but during construction, you have to physically pick up a 100-ton steel cylinder with a crane to erect it. You do that using heavy lifting lugs or trunnions, but you can't just weld a massive steel hook directly to the side of a thin-walled vessel, can you?
Absolutely not. If you weld a heavy trunnion directly to a 1-inch shell plate and then hook a crane to it and pull with 100 tons of force, the localized stress will instantly exceed the shear strength of the shell. The crane will literally tear the trunnion, along with a massive chunk of the vessel wall, right out of the side of the tank.
So how do you distribute that massive lifting force safely into the thin skin of the vessel?
You use reinforcing pads, or repads. Before you attach the trunnion, you weld a large, thick, circular or diamond-shaped plate of steel directly to the shell. This pad is carefully sized by the engineer, usually 0.75 to 1.5 times the thickness of the shell itself. Then, you weld the massive trunnion to the repad.
Ah, so the pad acts like a snowshoe.
Exactly. It takes the massive, highly concentrated point load from the crane and spreads it smoothly over a vastly larger surface area of the thin shell membrane. And when designing that attachment, the engineer isn't just looking at the weight. They have to calculate the shear stress on the welds holding the pad, the longitudinal bending moments trying to pry the pad off the shell, and the pinhole-bearing stress inside the trunnion where the crane's shackle pin is physically crushing against the steel.
It is an incredible amount of math just to pick the thing up. Okay, so the welder claims the beads are flawless. The engineer hopes the repad math is right. The vessel looks complete. But looking at it isn't enough. Now, the inspector steps in to find the invisible flaws. This brings us to the autopsy before the failure. Non-destructive testing, or NDT.
This is the validation phase. NDT is a suite of physical and chemical interrogations designed to prove the structural integrity of the steel without actually damaging it. And the first line of defense is always visual and dimensional inspection.
Visual inspection sounds simple, but the tolerances mentioned in the research are shockingly tight for something so massive. We are talking about vessels the size of a house. What is the inspector actually measuring?
They're looking for geometric deviations that ruin the stress math. For instance, they check for bow, which is how far the overall vessel deviates from a perfectly straight center line. On a vessel 10 meters long, over 30 feet, the maximum allowable bow might only be 6 or 7 millimeters.
6 millimeters of sag over 30 feet of welded steel. That is incredible precision. What else are they looking at?
They map the nozzle orientations. A massive pipe flange might need to connect to a specific pump on the site. The angle of that nozzle sticking out of the vessel must be within plus or minus 5 millimeters of the CAD drawing. They put straight edges across the flange faces.
Why the flange faces?
Because if the massive steel flange isn't perfectly flat and parallel to within plus or minus 2 degrees, the bolted gaskets won't crush evenly, and the volatile chemicals will leak out into the plant. And crucially, the inspector uses a flashlight to look for heavy grinding marks.
Wait, why are grinding marks dangerous?
If a welder laid down a lumpy, ugly weld, they might try to hide it by aggressively using an angle grinder to smooth it out and make it look pretty. But if they grind too deep into the base metal, they might reduce the wall thickness below the minimum T-C requirement we discussed earlier. A pretty overground weld is structurally thinner and weaker than an ugly, thick one.
Man, that's sneaky. But visual inspection only finds what is on the surface. How do we find the microscopic, surface-breaking cracks that are too small for the naked eye? The sources outline a method called dye penetrant testing, or DP. How does a chemical dye find a microscopic crack?
It utilizes the physics of capillary action. It is a brilliantly simple three-step chemical process. First, you thoroughly clean the weld area with a solvent. Then you spray the weld with a highly visible penetrating dye, usually bright neon red. This dye is formulated to have extremely low surface tension. You let it sit for 10 or 15 minutes. During that time, capillary action physically pulls the red liquid deep down into any microscopic invisible cracks breaking the surface.
But right now, the whole weld is just covered in red dye.
Right. So step 2 is wiping the surface completely clean with a rag and more solvent. You remove all the dye from the surface of the metal, but you leave the dye trapped deep inside the crack. Step 3 is spraying on a developer, which is a fine white powder suspended in a fast-drying solvent.
And the developer acts like a sponge.
Exactly. The developer creates a bright white background over the weld, and its porous nature physically wicks the trapped red dye back up out of the crack. The dye spreads into the white powder, painting a bright, glaring red line exactly over the location of the microscopic flaw. You can't miss it.
That is incredibly effective for any metal. But if you are working with ferrous metals, carbon steel, which is highly magnetic, you can use an even more advanced technique, magnetic particle inspection, or MPI. How does magnetism reveal a physical crack?
MPI is fascinating because it doesn't just find cracks on the surface, it can find cracks buried a few millimeters below the surface. The inspector uses heavy electromagnetic yokes to induce a massive magnetic field directly across the weld joint. The magnetic flux lines travel easily through the solid contiguous steel.
But what happens when those flux lines hit a crack? Because a crack is basically just a gap of air.
Air has a massive magnetic resistance compared to steel. So when the flux lines encounter a crack, they cannot easily cross the gap. Instead, the magnetic field is forced to jump up and out of the metal, traveling through the air around the crack before re-entering the steel. This creates what is called a magnetic leakage field right above the flaw.
How do you see a magnetic leakage field, though?
While the electromagnet is energized, the inspector sprays the weld with a fine mist of iron dust that has been coated in a fluorescent dye. The iron dust acts like thousands of tiny compass needles. They are drawn instantly and powerfully to the magnetic leakage field hovering over the crack. The inspector turns off the overhead lights, turns on an ultraviolet blacklight, and the iron dust packed into the crack glows a brilliant neon green, outlining the flaw perfectly.
That's like making the invisible forces visible. But DP and MPI only find flaws at or very near the surface. What about the deep interior of the weld? What if there is a massive slag inclusion buried 2 inches deep inside a multipass weld? For that, we need volumetric testing. The sources focus heavily on ultrasonic testing, or UT.
Yeah, UT is basically echolocation for steel. It uses the A-scope pulse echo method. A highly trained technician applies a coupling gel to the steel and slides a piezoelectric transducer over the surface. The transducer fires bursts of incredibly high-frequency sound waves down into the solid metal.
The sound wave travels through the steel until it hits a boundary.
Exactly. If the steel is solid, the sound wave travels all the way to the back wall of the plate, bounces off, and returns to the transducer. The machine displays this as a large spike on the screen at a specific time interval. But if there is a lamination hidden inside the plate, or deep crack buried in the weld, the sound wave hits that flaw and bounces back early.
And because it bounced back early, the machine knows exactly how deep the flaw is.
Yes. By calibrating the speed of sound in steel, the technician looks at the screen and says, I have a reflection coming back exactly 1.5 inches deep. By sweeping the transducer back and forth, they can map the exact 3D geometry, depth, and angle of the buried crack.
I understand the precision of UT, but I want to push back on this a bit. The sources also talk about radiography, RT, which is essentially taking an X-ray of a weld. If you can take a high-resolution, permanent photograph of the inside of the weld, why bother bouncing invisible sound waves around? Isn't a picture worth 1,000 echoes?
It definitely seems that way, but you have to understand the physical limitations of radiation. RT uses an X-ray tube or a radioactive isotope like iridium-192 to shoot gamma rays through the weld onto a piece of photographic film taped to the backside. RT relies on density differences. It measures how much radiation gets absorbed by the steel versus how much passes through.
So a void in the metal lets more radiation through.
Right. RT is absolutely phenomenal at finding volumetric defect things that take up physical space. A trapped bubble of gas like porosity or a chunk of glassy slag has much less density than the surrounding steel. The radiation passes easily through that void, hits the film, and creates a dark, easily visible spot on the negative. For volumetric flaws, RT is the gold standard.
But I hear a but coming.
But RT is incredibly poor at finding tight, plainer defects, like severe cracks. A crack is a structural failure, but it doesn't take up any volume. The two faces of the broken steel are pressed tightly against each other.
Oh, I see.
Yeah, if that tight crack is oriented perpendicular to the incoming radiation beam, the radiation just passes through the full thickness of the steel as if the crack wasn't there. There is no missing density, so the crack does not show up on the film at all. You could have a lethal crack running the length of the weld, and the X-ray would show a perfect, clear picture.
That's genuinely terrifying.
Which is exactly why UT is so critical. A sound wave doesn't care about density differences. It reflects off any physical boundary. UT will bounce an echo off a tight crack regardless of its orientation. Furthermore, RT involves highly hazardous, lethal radiation. When you X-ray a vessel, you have to clear the entire shop floor, halt all other production, and set up massive lead-lined exclusion zones.
While UT is safe.
Yeah, UT is completely safe. You can do it while the guy next to you is eating lunch. RT gives you a permanent picture of porosity, but UT finds the lethal cracks and tells you exactly how deep they are.
And the class of the vessel dictates how much of this expensive, time-consuming testing you actually have to do.
Precisely. If you are building a low-pressure water storage tank, the code might only mandate visual inspection and maybe 10% random UT spot checks. The risk is low. But if you are building a Class I lethal service vessel, say, a reactor containing pressurized hydrogen fluoride or anhydrous ammonia, where a leak means a toxic cloud over a city, the code will absolutely dictate 100% volumetric testing. Every single millimeter of every single pressure-retaining weld must be UT mapped and X-rayed.
All right. We've designed the architecture. We've rolled the steel, welded the seams, X-rayed the joints, and mapped the interior with ultrasound. The inspector has signed them out into paperwork. The vessel exists in physical reality. Now, we fill it up and try to break it. This is the moment of truth. Testing and failure modes. Let's start with the standard proof test, the hydrostatic test.
The hydro test is the final exam before the vessel leaves the shop. The procedure is conceptually simple. You cap all the nozzles. You fill the entire massive vessel completely to the brim with water. It is absolutely critical that you vent every single pocket of atmospheric air out of the highest nozzles. Once it is completely solid with water, you hook up a high-pressure hydrostatic pump and you slowly squeeze more water into the vessel until the internal pressure reaches 1.25 or sometimes 1.5 times the maximum allowable working pressure the vessel was designed for.
The obvious question is, why water? Why deal with thousands of gallons of heavy, messy water? Every machine shop has massive industrial air compressors. Why not just pump it full of compressed air? It's lighter, it's faster, it doesn't rust the steel.
It's an incredibly important question, and the answer is pure physics regarding stored energy. Water is fundamentally an incompressible fluid. If you have a 10,000-gallon tank completely full of water, and you use a pump to pressurize that water to 500 psi, the actual volume of the water barely changes at all. You are only adding a few extra cups of water to spike the pressure.
So the energy isn't stored in the fluid itself.
Exactly. The energy is stored purely in the slight elastic stretching of the steel walls. So if the vessel has a critical flaw that the X-rays missed and it fails during the hydro test, the outcome is dramatic but localized. The steel cracks, a small jet of water squirts out, the steel instantly relaxes back to its original shape, and the internal pressure instantaneously drops to zero. The event is over in a fraction of a second. The floor gets wet, but nobody dies.
Now contrast that with the pneumatic test using compressed air. Air is a gas. It's highly compressible.
If you fill that same 10,000-gallon tank with compressed air to 500 psi, you are taking an astronomically massive volume of atmospheric air and violently crushing it into a small space. That highly compressed gas acts exactly like a massive coiled mechanical spring. It holds a terrifying amount of potential energy.
And if the vessel cracks under pneumatic pressure?
If a crack initiates, the pressure does not drop instantly. The highly compressed gas violently expands, trying to return to its massive atmospheric volume. That rapidly expanding air acts as an explosive charge. It catches the edges of the crack, rips the steel wide open, and literally blows the vessel into fragments, launching multi-ton pieces of jagged steel shrapnel across the shop floor at supersonic speeds. You have effectively manufactured a massive bomb.
Oh.
Wow! Pneumatic testing is incredibly lethal and is avoided at all costs. It is only permitted if the vessel simply cannot tolerate water for process reasons like cryogenic systems, and it requires extreme safety barricades and 100% perfect NDT beforehand.
But the sources do mention one specific scenario where air is used to test a vessel safely. Vacuum leak testing. How does that work without building a bomb?
It works because the pressure differential is reversed, and the maximum energy is capped by the atmosphere. For equipment like steam condensers that operate under vacuum, a high-pressure hydro test doesn't actually prove the vessel won't leak air inward during operation. So you pull a coarse vacuum on the vessel, essentially sucking the air out.
And why?
You seal the valves, and you attach a highly sensitive pressure gauge. Then you just watch the clock, you measure the leak rate over time, you calculate the change in internal pressure, multiply it by the volume of the vessel, and divide by the time elapsed. If the vacuum holds, the seals and welds are tight. If the pressure slowly creeps up, air is leaking in through a microscopic flaw.
Okay, so we've run the hydro test, but testing is ultimately about surviving failure. And the sources break down the grim realities of failure into 8 distinct categories. I want to walk through these, not as a textbook list, but to understand what they actually look like in reality. The first one we already touched on, elastic deformation.
Right. Elastic deformation is the geometric instability we discussed with the soda can and external vacuum pressure. The critical thing to understand here is that the metal itself didn't break. The atomic bonds didn't fail. The geometry simply buckled. The vessel deformed elastically, meaning if you could magically push it back out, the steel would still be fine. It is a failure of shape, not material.
The second mode is terrifying because it happens suddenly, brittle fracture.
Brittle fracture is the catastrophic explosive failure we discussed regarding the fracture mechanics paradox. The crack runs at the speed of sound. And the terrifying part is that brittle fractures often happen during the hydro test right on the shop floor.
Wait, if the vessel passes the X-rays, why would it shatter during the water test?
Temperature. It all comes back to the nil ductility transition temperature, or NDT. In the winter, the water pumped into the vessel from the city mains might be very cold, say 40 degrees Fahrenheit. If the carbon steel alloy used has an NDT of 50 degrees, pouring that cold water in instantly transitions the steel from a ductile sponge into brittle glass.
So when the pressure rises,
When the pump ramps the pressure up, any microscopic flaw becomes the origin point for a massive brittle fracture. The entire vessel shatters before it even reaches design pressure.
that segues perfectly into a concept the engineers use to prevent that exact scenario. MDMT, the minimum design metal temperature. How do they design around the cold?
The MDMT is the absolute lowest temperature the vessel steel will ever experience, whether from the fluid inside or the winter weather outside. To ensure the metal remains ductile at that freezing temperature, the code typically requires the foundry to perform expensive Sharpie V-notch impact testing on the raw steel plates at that specific temperature.
They literally swing a heavy pendulum at a notched piece of the steel to see how much energy it takes to snap it in the cold.
Exactly. But impact testing costs money and delays production. Engineers hate paying for it, so the code offers a mathematical loophole. You can avoid impact testing if you dramatically lower the stress in the metal.
And how do you lower the stress?
You artificially increase the thickness of the component. If the wall is vastly thicker than it needs to be, the operating stress is so low that the risk of a crack propagating is minimized, even if the metal is cold and slightly brittle. The code allows you to buy your way out of impact testing by buying vastly thicker steel.
The third failure mode is excessive plastic deformation.
Right.
This is the classic cartoon failure.
Right. The internal pressure vastly exceeds the yield strength of the steel. The metal physically stretches, yielding plastically. The vessel swells up, bulges outward like a balloon, the wall thins out, and eventually it just tears open.
Now, the fourth mode sounds insidious. Stress rupture or creep. What is creep? It sounds slow.
It is agonizingly slow, and it only happens at high temperatures. Think of a vessel operating at 1,000 degrees Fahrenheit for 20 years. The internal pressure is well below the yield strength. The math says it's perfectly safe. But at those extreme temperatures, the atomic lattice is vibrating violently.
So the metal itself is moving.
Over years of constant tension, the microscopic grain boundaries inside the steel literally begin to slide past each other. The solid steel slowly, imperceptibly stretches like warm taffy. The vessel gets permanently longer and wider over decades until the wall thins out so much it finally ruptures.
That requires constant vigilance over decades. The fifth mode is plastic instability. That sounds like a fatigue issue.
It is incremental collapse. It's not a single massive overpressure event. It's cyclical. Imagine a vessel that cycles from 0 psi to max psi every single day. Due to complex geometry around a nozzle, there is a tiny localized area where the stress exceeds the yield point just a tiny bit during every cycle. Day 1, the metal stretches a microscopic fraction of a millimeter.
And day 2?
Day 2, it stretches another fraction. It never springs back. Over thousands of cycles, this localized plastic deformation accumulates, ratcheting up until that section of the vessel becomes completely unstable and tears.
Which is closely related to the sixth mode, high strain, low cycle fatigue.
Yes, but this applies to highly ductile materials subjected to massive extreme strain amplitudes. Instead of taking thousands of small cycles, the material undergoes massive stretching and compressing. The ductile metal absorbs it for a while, but the severe strain tears the crystal lattice apart, leading to massive fatigue cracking after relatively few cycles.
Now we get into the chemistry. The seventh mode is stress corrosion cracking. This sounds like an unfair fight.
It is the ultimate ambush. Stress corrosion cracking requires three specific conditions to exist simultaneously. You need a susceptible material, you need an active tensile stress pulling on that material, and you need a highly specific corrosive environment. The terrifying part is that the corrosive environment might barely affect the metal if there was no stress applied.
Give me an example of that chemical lock and key mechanism.
Chlorides and austenitic stainless steel. You can drop a piece of 304 stainless steel in warm chloride water, and it will sit there relatively happily. But if you take that same piece of stainless, bend it into a U shape to create massive tensile stress, and then put it in the chloride water, the chlorides will aggressively attack the grain boundaries, specifically where the tension is highest.
It zeroes in on the stress.
The chemical attack literally unzips the atomic bonds pulling against each other. A thick plate of stainless steel will crack completely in half in a matter of hours. Caustic environments do the exact same thing to carbon steels.
And the final, eighth mode, is the absolute worst of both worlds, corrosion fatigue.
It is a synergistic nightmare. You take the mechanical trauma of cyclic fatigue loading, the constant stretching and relaxing, and you drop the vessel into a corrosive environment. The two mechanisms accelerate each other logarithmically. The corrosion eats microscopic pits into the surface.
And those pits become stress risers.
Those pits act as massive stress risers. The cyclic fatigue load concentrates on those pits, rapidly tearing cracks open. The corrosive fluid immediately rushes deep into the fresh, unprotected crack, eating away the tip and making it sharper. It's a self-feeding loop of destruction that drastically, unpredictably slashes the lifespan of the vessel.
I want to pull all of this together and contextualize the hydro test based on these 8 horrifying ways a vessel can die. The expert analysis of the hydro test from the sources is the most sobering reality check of this entire deep dive.
It is, because clients and even young engineers look at a successful hydro test and they celebrate. They think the vessel held 1.5 times its design pressure. It didn't leak. It is perfectly safe.
But it's an illusion of absolute safety.
Exactly. The hydro test is a very limited static proof. All a successful hydro test proves is that on that specific Tuesday afternoon, sitting on the shop floor at ambient temperature, the vessel possessed the gross structural integrity to resist the principal static membrane stresses of an overpressure event. It proves the welder didn't leave a massive hole in a seam. It proves the plates are generally thick enough.
But it proves absolutely nothing about the future.
Nothing. A successful hydro test does not prove the vessel will survive 30 years of cyclic pressure fatigue. It does not prove the steel won't slowly succumb to high temperature creep over a decade. It certainly does not prove the vessel won't be torn apart by stress corrosion cracking next month when the chlorides are introduced. It is a baseline static test. It is not a guarantee of operational lifespan.
I look at it this way. A hydro test is like a 1-rep max deadlift at the gym.
Yeah.
Just because you can load the bar up and pick that massive weight off the floor once without breaking your back, it absolutely does not mean your spine won't slowly degenerate and fail if you try to lift a slightly lighter weight every single day for a decade, especially if you're standing in an acidic swamp while you do it.
That is precisely the reality. The hydro test proves you survive day one. The material selection, the pitting index, the fatigue analysis, the corrosion allowances, and the flawless execution of the WPS by the welder. That is what gets you to year 30.
Which leaves us with a final, slightly provocative thought to ponder. We've spent this entire time talking about the incredible precision of modern engineering. Today, we have finite element analysis CAD software that can model stress gradients down to the millimeter. We have laser-guided plasma welding. We have ultrasonic phased array mapping that can see a microscopic flaw buried inside 3 inches of solid steel.
Yeah, we have unparalleled visibility into the physics of the material.
But back in the day, the engineers who built the first massive industrial boilers and chemical columns didn't have these tools. They couldn't calculate the exact localized shear stress around a nozzle. So what do? They over-engineered everything. They built in massive ignorance, so they built incredibly heavy. They used incredibly thick plates and giant, sweeping, highly conservative safety factors.
They build battleships to hold steam.
Exactly. So here's the question for the modern designer listening to this. Are highly optimized, mathematically perfect, and vastly thinner modern designs actually leaving us less margin for error on the shop floor? If a modern vessel is designed right to the absolute ragged edge of the yield strength just to save weight because the computer simulation says it is technically safe, what happens when reality sets in?
That's the terrifying part.
Does a single moment of human error by a tired welder or a slight misalignment on the rollers instantly become a catastrophic event because the safety net of extra thickness is gone? Does our advanced technology make us fundamentally safer, or has it just made us more arrogant, pushing the materials closer and closer to the edge of disaster? Something for you to ponder the next time you strike an arc or finalize a CAD drawing.
The margins are undeniably tighter today. The precision is higher, the efficiency is beautiful, but the safety net is much, much thinner.
Your GPA won't save you when the part fails. Only your scars will. Thank you for listening. Don't forget, if this helped you even a little, please tell us. We're putting this out for free, no paywall, no subscription, nothing locked behind a card. That only works if we know it's actually reaching and teaching. If you're on a journey trying to figure this stuff out and this gave you clarity you weren't getting anywhere else, drop a like, leave a comment. It takes 2 seconds on your end, but it tells us this is worth continuing. Also, don't forget to check out our YouTube.